Thank you very much, and I apologize for the vague title. But today I'll tell you about two pieces of upcoming work. The first will be about reflection positivity in the quantum gravity Hilbert space, and this is work with Henry Lin, Gabriele Diubaldo, and Cynthia Yan. And the second, which was partly motivated by the first, will be about revisiting the no-boundary proposal from the modern path integral perspective, and this is with Ahmed, Stefano, Raphael, Adam, and Arvin. Great. So in recent years, the gravitational path integral has successfully explained why gravitational theories and the objects within them, such as black holes, are described by ordinary quantum systems. So for instance, using the path integral, we've recovered the page curve, we've recovered a lot of information about the spectral statistics of black holes, and we've even understood some probes of the black hole interior, such as the size of the interior of an Einstein-Rosen bridge. And all of this was done by computing overlaps between different black hole states in extreme regimes. So understanding overlaps from the gravitational path integral probably has been one of the most important developments in the past years. Now, the objective today will be to understand whether this modern framework of the path integral can also be used to understand probabilities in more complicated settings, such as in cosmological spacetimes. And more specifically, I'll try to address the following three questions. The first question that I will address is whether there is some positivity constraint that the path integral has to satisfy in order to define a Hilbert space of closed and open universes. So I'll try to make a wish list of what the path integral needs to satisfy. Sort of like the wormhole bootstrap that Pratik talked about this morning. The second question is whether the path integral truly satisfies these conditions in the gravitational effective field theories that we've studied so far. So, we all know about JT gravity, but people have actually studied a bunch of wormholes even in higher space-time dimensions, and you could wonder whether the conditions that we'll derive in one are actually satisfied. Now, the surprise will be that they are actually satisfied in closed universes in all the examples that we found. And personally, I found that very surprising. And that motivates a case study. If we can actually define a Hilbert space, then we can apply Bohr's rule and study transition probabilities. So we could ask, what is the transition probability from the no boundary state to a different state when using the modern framework of the path integral? And the important question is whether wormholes, the type of wormholes that were important in the page curve and for all the other effects, are also important in this context. So to answer all these questions, we first need to talk about the framework, and I'll talk about the framework of the path integral. So the path integral is a map from boundary conditions to complex numbers. So in the path integral, we sum over all geometries with a given set of boundary conditions that could be specified by, for instance, the induced metric and the values of all fields on some boundary manifold sigma. Now, sigma could or might not contain multiple components. So the boundary condition on each component that I'll call sigma, each connected component that I'll call sigma I, I'll just label by ji. So what exactly are we summing over? And how is this complex number related to inner products? Well, to obtain this complex number, z of j, we in principle have to sum over all geometries. These geometries might be both connected and disconnected in the sense that the space-time might connect the different disconnected boundaries or not, and might contain both on-shell but also potentially off-shell contributions. It might contain real contributions, complex contributions. The rules are slightly unclear at this point. In addition to these contributions, in principle, we should also sum over disconnected closed spacetimes. By disconnected closed spacetimes, I just mean spacetimes that are not connected to one of the boundary whose boundary condition was ji. Now, just like in QFT, the sum over such diagram ends up being exponentiated. If I sum over one closed spacetime, why not sum over 2, 3, so on and so forth? And accounting for all symmetry factors, you get this exponential from the sum over all disconnected closed spacetimes. So how is this complex number z related to an inner product? And for that, we'll take some inspiration from quantum field theory. So in quantum field theory, boundary conditions define states, and the path integral can be used to compute the inner product between states. Here is a very simple example on a torus times an interval that's supposed to represent time, where I set the value of the field at the bottom of the torus, on the bottom torus to be phi1, and at the top torus to be phi2. This would compute this overlap. This path integral would compute this overlap in Euclidean signature. So what are the boundary conditions that we can use in gravity? Well, we can, for instance, impose boundary conditions on closed manifolds. This would create a closed universe state that I'll label by z of ji. This does not have to be necessarily an asymptotic boundary. But I could also create open manifolds that I'll label by this fancy j, a psi of fancy j. The boundary conditions are labeled by fancy j. And again, this does not necessarily need to be an asymptotic boundary, but we can consider it as such. Importantly, this ji's themselves have a boundary that I'll call partial ji. This is the boundary of the boundary. And thinking about that will tell us a bit about how to glue these states. In addition to this, there's an additional final state, which is a no boundary state, which I'll call the Hartle-Hawking state. It's a state that's not specified by any boundary conditions. I don't insert any additional information in the path integral. So this defines what the kets are. To define the bras, you have to define an antilinear operation on these boundary condition that if the manifolds are orientable, it flips the orientation of the boundary and takes the complex conjugate of the boundary condition roughly. So you can define this on closed universes and open universes. It doesn't do pretty much anything to the Hartle-Hawking state. Now, this is just a guess at this point. We're not sure whether this antilinear operation is sufficient to define a positive definite inner product, and that will be a big part of the talk today. So finally, how do we go from boundary conditions to inner products? Well, once again, we take inspiration from QFT, and we use the fact that in gravity, the Wheeler-DeWitt constraint, the Hamiltonian is 0 because of the Wheeler-DeWitt constraint. So the inner product between any states is given by any filling in between these boundary conditions. So here's, for instance, I listed the contributions to the inner product of two closed universe states. And for open universe states, we have to glue the open boundaries on their common boundary of a boundary. And we can only do that if the boundary condition partial J1 star agrees with the boundary condition for partial J2. So for instance, I can only perform this gluing if the geometry in the bra and the geometry in the ket is the same on the common part of the interval. And this gives me a closed space-time that has boundary condition J1, say, where J1 is defined by this equation. And the path integral just computes this inner product by computing the path integral with these boundary conditions. And none of these inner products are normalized, and this will be very important when discussing the Hartle-Hawking state shortly. So at this point, once we start considering more complicated boundary conditions with more disconnected boundaries, there's an ambiguity that arises. So for instance, consider these types of boundary conditions where there are in total 2n boundaries. This type of boundary conditions arises if we think about the inner product zj1 through zjn with zj1 tilde through zjn tilde. But the same boundary condition also arises if we think about a product of inner products. They both share the same boundary conditions. So there's two different ways about thinking about the geometries that contribute to this path integral. And this will give two different approaches. The first approach is what I'll call the statistical approach, in which we'll think about this number z as computing the statistics of individual inner products or of products of inner products. So we can think about this number z as either computing the statistics of a single inner product or the statistics of n inner products. And then we can try to use these statistics that the path integral computes to try to infer properties of the underlying Hilbert space H alpha. So that's option one. Option 2 is pretty much what Marolf-Maxfield did, in which they said that this number is associated to a single inner product, zj1 through zjn tilde. And this inner product is different than the product of inner products, namely in the bottom line, you only include connected contribution between j1 and j1 tilde, all the way through jn and jn tilde. So each path integral computation computes a single overlap and not statistics of a product of overlaps. As Daniel advertised yesterday, the Hilbert space, we'll see that for closed universes, the Hilbert space on the left will kind of be trivial, but the Hilbert space on the right is not necessarily trivial. Great. A similar interpretation can be given to open universes. If we consider the possible inner products of n universes, we could say that the same boundary conditions either compute the statistics of n overlaps in an open universe, or it could just compute a single overlap amongst n open universes. Now, this is the framework. And we could ask whether this framework is self-consistent. Namely, are the complex numbers that the path integral computes truly consistent with both interpretations, both with the statistical interpretation and with the Marolf-Maxfield interpretation? In both interpretations, there is some implicit assumption of reflection positivity. And that's because, when we compute an inner product, if you compute an inner product with itself, or the average of that, you should get a positive number. And that's not clear in gravity. In QFT, this can be easily derived. So for instance, if you take a manifold might be symmetric with respect to a plane. If you perform the path integral above the plane of symmetry and below the plane of symmetry, then the two results will be complex conjugate to each other. And if you integrate overall field values on the plane of symmetry, then you'll find that the Euclidean path integral on the manifold that is reflection symmetric is positive. In gravity, this is very unclear. There might be some geometry that is reflection symmetric. But, because we sum over geometries, there is not a common plane of symmetries amongst all geometries, and not all geometries will be reflection symmetric. Moreover, these boundary conditions J that I mentioned don't actually prepare all the states in the path integral. I should also ensure that linear combinations of states created by these boundary conditions produce states that have a positive norm. So with this, I'll try to answer what the positivity constraints on Z are for open and closed universes. And in parallel to presenting these positivity constraints, I'll describe how these are satisfied in JT gravity, just so that you have a working example. Now, the first positivity is the simplest, maybe most trivial positivity rule that I can discuss. And that's the positivity of the norm of the Hartle-Hawking state. So in both approaches, the norm of the Hartle-Hawking state is given by the exponential of a sum of close connected spacetimes, spheres, tori, whatever contributes. And if I want this to be positive, this is only the case if sphere plus torus plus so on is a real number. Now, I want to point out that I don't know whether in, let's say, positive cosmological constant, the sphere partition function is real. That depends on the choice of contour, and this was discussed by a lot of people lately. But I wanted to point out that this constraint is already different than the constraint that people typically discuss, in which they think about the sphere as capturing the trace of some identity operator in some underlying Hilbert space for de Sitter. Namely here, the constraint that comes out is that the sphere has to be positive, whereas here the constraint that comes out is that the sphere has to be real. This constraint on the Hartle-Hawking state is somewhat of a formality. Instead of constraining from now on the inner products between the different closed or open universes, we can define inner products that are normalized by the Hartle-Hawking state, in which case this contribution completely drops out. So at the end of the day, I can actually define a Hilbert space with or without satisfying this criterion. But I just wanted to mention it at first. Now, what's the simplest constraint if I think about the closed universe state? Well, let's prepare a state, a bra and a ket, that each contain a single closed universe. Well, in principle, any linear combination of bras and kets should be positive. And the inner product between z of j1 and z of j2 is computed by this complex number, z of j1 star j2. So because this is positive for any function psi, this implies that these complex numbers, you could think about this as a matrix of complex numbers. This matrix has to be semi-positive definite. And this is a very non-trivial constraint that I think is related to the constraint that Hong alluded to a couple of talks ago. Now, I just wanted to point out that the same constraint can be derived from the statistical approach. Here I talked about the Marolf-Maxfield positivity, but in the statistical approach, this is just basically equivalent to the Hamburger moment problem of the underlying statistical ensemble. So you can take these numbers, z alpha j1 star times z alpha j2, form a positive semi-definite matrix. And if you average over such matrices with a positive probability measure, then you would generate, again, a matrix that has to be positive semi-definite. So in both approaches, we get the same positivity constraints that we have to satisfy. So even if you don't believe in Marolf-Maxfield, or if you don't believe in the statistical, but you believe in the statistical approach, or vice versa, you should satisfy the same constraints. Great. So notice that in this approach, we're only constraining the probabilities in this ensemble to be greater than 0, or assuming that. But we're not imposing any constraint on these numbers, z alpha. And what I take that to mean is that we're looking at a probabilistic ensemble of theories, but we're not providing any constraint on the theories that describe the closed universe Hilbert space. They might be unitary, they might be non-unitary. I don't know. Now, in both approaches, we can get a cleaner, slightly stronger constraint by inserting a projector onto the orthogonal subspace to the Hartle-Hawking state. Now, because a projector is a positive definite, this still has to be greater than 0. Sorry, I forgot a pi. There. This still has to be greater than 0 for any psi. And once you insert a projector onto the space that's orthogonal to the Hartle-Hawking space, you're only left with connected contributions, connected wormhole contributions. Compared to the previous slide, I got rid of these disconnected contributions. So the stronger constraint that we have to satisfy is that the matrix formed out of wormhole entries has to also be positive semi-definite. Let me just give you an example of what that means. So let's take our manifold sigma to be S1 cross SD minus 1. So I'll discuss two copies of S1 cross SD minus 1. One constraint is that the diagonal is positive. Any positive semi-definite matrix has a positive diagonal. This implies that the spectral form factor, the contribution from wormhole to the spectral form factor has to be positive. That's sort of an easy constraint. Even that, it's kind of complicated because you have matter one-loop determinants on top of this wormhole background. So it might get confusing if you have fermions, what the sign is. But you could imagine how you might satisfy this. The more complicated constraints comes if you look at submatrices of this kernel. If you look at a submatrix of this kernel, you find that, for instance, the product of two wormholes with identical boundary conditions has to be greater than the absolute value squared of a wormhole with the two different boundary conditions, beta 1 and beta 2. Since everyone loves JT gravity here, let's just do a sanity check. In JT gravity, the connected contributions from wormhole has this formula, and you can find that indeed it's satisfied. It's satisfied. Well, you can check that this kernel is positive definite very explicitly, but you could also check that this 2x2 matrix is explicitly satisfied. That's much easier. It's just this inequality just becomes this inequality, which I believe you can all immediately see is satisfied because beta 1 minus beta 2 squared is greater than 0. Now, it turns out that other boundary conditions can actually provide new constraints, but I don't have time to talk about this. You could ask me in the discussion. We can also we can ask whether we can obtain additional constraints from states prepared with more complicated closed slices. So for instance, what if instead of inserting one closed universe, we prepare states with two closed universes, like here? It turns out that the best you could do is constrain the kernel in J1, J2 versus J3, J4 to be semi-positive definite as a kernel in this variable, in this pair of variables and this pair of variables. Now, it turns out that if these contributions dominate, these are just products of the wormholes that we saw previously, this constraint is automatically satisfied if we satisfy the previous constraints. So we do not obtain any immediate, very valuable constraints. We believe that there are no inequalities that only involve connected wormholes with more than two boundaries. Well, you could ask me more about this at the end. It's actually kind of an interesting point. Now, what if instead of imposing positivity for closed universes, we impose it for open universes? So if I think about the inner product between two open universes, I get this complex number that's defined on the union of the two boundary conditions. And I can view this complex number as a kernel in J1 and J1 tilde. And this kernel, again, has to be semi-positive definite. And more generally, you can construct a kernel in n and n variables, and this also has to be positive definite. What does this concretely imply? Well, let's take the example where these states are what we traditionally call thermal field double states, states prepared on an interval times SD minus 1. In that case, that kernel is actually only the kernel with n equal 1, only depends on beta 1 plus beta 2, the two lengths of the interval. And the constraint that we obtain is that this kernel as a kernel in beta 1, beta 2 has to be semi-positive definite. And one can prove, this is called the Bernstein-Wilder theorem, that this is equivalent to proving that the average density of states is positive. And this is also equivalent to proving that z of beta is a completely monotonic function. This is what a completely monotonic function means. If you look at n boundaries, you get the slightly stronger constraint. But in either case, these constraints are completely different than what we saw for closed universes. Here, we're saying that we're looking at a probabilistic ensemble of unitary theories, because the density of states has to be positive in a unitary theory. Whereas previously, there is no constraint on the unitary on the theory. The only word that was important previously was probabilistic. Now, it actually turns out that I can glue these open universes in a more complicated way and get additional constraints. So we can consider linear combinations of states in which partial J are connected in different ways. So let me give you an example. You can prepare a state psi1 with two open universes that look like this, or a state psi2 with two open universes that look like this. Here, notice that the boundary of J1 is the first boundary of a boundary is connected to the second boundary of a boundary, while here, the first boundary of a boundary is connected to the fourth boundary of a boundary. So what happens if I try to impose that any linear combination of psi1, psi2 is also a positive semi-definite matrix? Well, let's just, we can form this matrix of overlaps and impose that it's positive semi-definite. This just amounts to imposing that the partition function with two copies of beta is greater than the partition function of 2 beta. For those of you that have good memory, you've encountered this inequality before this morning, right? It's exactly what Stefano and Pratik talked about. It's the same as the constraint that the semi-quenched entropy is positive. And this type of inequality is only visible after a genus resummation. If you want to check that it's true, you have to perform a complete genus resummation in JT gravity. And this inequality also is only valid if your spectrum of energies is discrete. So actually imposing these types of positivity constraints imposes an even stronger constraint, namely that we're looking at a probabilistic ensemble over unitary theories with discrete spectrum. So closed universe just means probabilistic. The more trivial gluings in an open universe means probabilistic ensemble over unitary theories. And when you include even more complicated gluings, you also impose a discrete spectrum. There might be other inequalities that are even stronger than these 3 words, but we don't know exactly what they are. Now, these are the inequalities that we've derived, and we can ask whether the path integral actually satisfies them in more complicated examples. So the examples that I'll discuss will mostly focus on pure 3D gravity. We've saw that they're satisfied in JT gravity. And we're going to look at both on-shell and off-shell geometries. I'll also mention matter-supported wormholes in ADS 3, 4, and 5. Before I go for the examples, I want to make a slight sociological comment. So let's contrast the constraints for closed and open universes. Now, in the context of ADS CFT, the path integral inner product for open universes should approximate the CFT inner product, at least at leading order in G Newton. So that means that these positivity constraints should follow from the CFT Hilbert space positivity constraints, so they should be at least approximately satisfied. In contrast, there's not a similar argument for closed universes that's on solid footing. So if you're really a skeptic of everything that I just presented, this is the way to go and try to disprove it. You'll come to me and compute some wormholes and tell me, oh, look, it doesn't define a Hilbert space because your inequalities are not satisfied. So you should be extremely surprised if the closed universe inner product turns out to be positive definite. So to kind of take a skeptical point of view, I'm going to start with an open universe constraint. And this is something that all of you probably know. Namely, let's look at the norm of the thermal field double state in pure gravity in ADS-free. So this is a setting where some of you at least might know that positivity fails. Namely, consider the overlap of two states that are defined on an interval times S1. These are essentially dual to thermal field double states. The inner product between two such states produces a partition function. And in 3D gravity, we know how to compute this partition function. It's a sum over vacuum characters, where the sum is over the mapping class group of the now closed boundary, which is a torus. Now, notice that here, these T stars and T bar stars appeared. That's because when you look at the bra, you have to complex conjugate the boundary condition, and the antilinear operation that I mentioned at the beginning of the talk sends tau to minus tau star and tau bar to minus tau bar star. It doesn't quite complex conjugate it. So this is how you obtain these boundary conditions. And this product of vacuum Virasoro characters itself is a trace over some Hilbert space, is the trace of the vacuum Virasoro representation. And it's guaranteed to be positive only in the regime where the SL2Z transformation gamma acting on tau minus tau star or on tau bar minus tau bar star, sorry, there's a bar missing here, is a purely imaginary number. This is only true for the identity transform and an S transform, generically. So the problem is that there actually exists a regime, it's this regime that I wrote over here, where the vacuum Virasoro character with the identity and the vacuum Virasoro character with the S transform go to 0. And what remains that dominates in the sum has no guarantee to be positive, and one can choose tau and tau bar in such a way that it actually goes negative. So the term that dominates is negative, and the partition function becomes negative in this regime, which consequently also means that the density of states becomes negative. So this is just the Maloney-Witten negativity rephrased as the norm of a thermal field double state. It turns out that a similar argument can be used to show that the negativity persists in some regimes on a genus G surface. So we can cut the reflection symmetric genus G surface around this plane of reflection, and one still has to sum over the mapping class group images of a genus G surface, and in some regimes you can show by a similar logic that the same negativity occurs. Now, there have been numerous proposals of how to cure this negativity. You could add matter fields, string states, or off-shell geometries, and it will be interesting to see if these cures the negativity for all values of G. Now, one inequality that I'm fairly confident these solutions won't cure or will not satisfy is the following. It's the inequality that was discussed this morning by Pratik and Stefano, namely that z of beta squared in a sector with fixed angular momentum is greater than z of 2 beta. So even if we cure the negativity of the partition function, I doubt that we will cure the negativity of norms for these more complicated states. Now, to really satisfy this inequality, as we saw this morning, we need a very fine understanding of wormholes and 3D gravity. So what do we know about wormholes and 3D gravity? And do they satisfy the closed universe constraints? Well, one wormhole that we know was computed by Cotler and Jensen. And it's also given by a sum over SL2Z. SL2Z is, again, the mapping class group of the torus. Here, the sum over SL2Z corresponds to relative mapping class group transformations between the left and the right boundary of the torus. So you get this answer. Now, because we have a sum over SL2Z, but each term in the sum has no scaling with the central charge of the CFT, with G Newton, we're actually in a very precarious situation. This is because if one of the terms turns out to be negative and dominant, then essentially we would have a kernel that would have a negative eigenvalue that would be order 1. And you wouldn't be able to find some solution due to some other off-shell geometry or anything like that that would cure this problem. The only way to cure this problem is if you argue that this wormhole is not the dominant one. But I think we believe it is at this point. Now, it turns out that we can actually explicitly diagonalize this kernel based on symmetries. I won't go into the details of that, but it essentially can be diagonalized into a basis of eigenfunctions that are given by Eisenstein series and Maas-Kasp forms. It's due to the SL2R invariance of the initial seed and due to the fact that this wormhole is invariant under independent SL2Z transformation of tau 1 and tau 2. Now, in this formula, in which these eigenfunctions are actually form an orthonormal basis, we can look at the eigenvalues and ask whether they're positive or negative. And miraculously, they come out positive, which means that any matrix that you would form out of these wormholes is actually positive definite, which is what we wanted. You could look at a more complicated wormhole, namely at on-shell wormholes in ADS-free. These have recently been understood. These are wormholes that were first discussed by Maldacena and Maus. But this have been recently understood in the language of Virasoroty QFT. So we know how to compute these overlaps very, very precisely for any boundary and any boundary moduli, tau 1 and tau 2. Now, the problem with these wormholes is that the overlap between closed universe states is not given by a single overlap in a VTQFT, a well-defined Hilbert space, but it's instead given again by an infinite sum, where the sum is over the mapping class group of the boundary. Now, beautifully, what appears in this infinite sum is the overlap between tau 1, the modulus on the left side, and tau 2, with a unitary representation of the mapping class group inserted in between. So this result can be viewed as a group averaging. The right-hand side is basically a group averaging over the mapping class group of one of the two boundaries. Now, because inner products are positive in the Virasoroty QFT Hilbert space, it turns out that the inner product that you obtain after this group averaging procedure is also positive. This is essentially because the sum over all unitary representations of a group element of the mapping class group is basically inserting a projector onto singlets of under the mapping class group. Now, since the mapping class group is typically non-compact, this is subtle, but we can actually check this positivity explicitly in several examples. So again, we obtain positivity. Even more extreme is that we can obtain positivity for wormholes that have matter moduli. So we numerically checked that wormholes with matter moduli, you can fix the boundary conditions of a matter field to be phi 1 and phi 2, phi 1 on the left and phi 2 on the right. And you check that you can check that this matrix of wormholes is positive semi-definite in ADS 3, 4, and 5. Ask me after if you're interested. So in all these examples that we tested, the path integral yields a well-defined Hilbert space of closed universes, or it solves the Hamburger-Mohmann problem for the statistics of inner products. So depending on your preference, you can take your pick. This is very encouraging. Because of this, we can now apply Bohr's rule to compute transition probability between these two different states, and we'll look at a case study. What is the transition probability from the no boundary state? The most trivial example is the one in the statistical approach, which was kind of reviewed by Daniel yesterday. So what's the transition probability in the transition? And the statistical approach is exactly what you expect. You want to compute the average of this ratio of inner products. Well, computing an average of a ratio is typically complicated. So instead, we can do something slightly different. We can compute the ratio of averages, for instance, the ratio of each average. But the boundary conditions that I have to set up in the path integral for the numerator and denominator are exactly the same. So therefore, this ratio of averages is 1. And moreover, if you look at the nth moment of the numerator and the denominator, this is also 1. And in turn, it turns out that if you prove all this, you could also prove that the average probability itself is also 1. And this is just a simple signature of the fact that the Hilbert space whose inner product we're averaging over is one-dimensional. That's the downside of the statistical approach. You don't get interesting results, even in the Hartle-Hawking state. Now, in the Marolf-Maxfield approach, the Hilbert space is no longer one-dimensional, so there's hope. We should get a non-trivial transition probability. So here are all the ingredients to compute the transition probabilities, all the inner products that you need to know. Let me unpack this for just a few minutes. The first is that in the overlap between Z of J and Hartle-Hawking, there's a contribution that comes from a saddle that has no additional boundary. In the case of de Sitter space, it would have only a future asymptotic boundary, or in the case of ADS, it might have a Euclidean asymptotic boundary. This is essentially the same contribution that people encountered in the wave function in the old no-boundary proposal. Now, the difference between the statistical approach and the Marolf-Maxfield approach turns out to be where the connected contributions sit in these inner products. Namely, in the Marolf-Maxfield approach, there's only a connected contribution in ZJ, ZJ, but there's no connected contribution in ZJ with HH on. The more important difference between the Marolf-Maxfield approach and the old no-boundary proposal comes in the first term, the normalization term for Z of J. In the old no-boundary proposal, people usually canonically normalized these states, which means that, roughly speaking, they only consider the connected contributions between two different slices, which is a delta function. But that's actually a subdominant contribution compared to the disconnected contribution that actually dominates. And moreover, in the old approach, the normalization of the Hartle-Hawking state was different. It was not an exponential of a sphere, it was the sphere itself. Now, if we take all these new ingredients together and actually compute the probability, the contribution of closed disconnected space-time just cancels out. And you're left with 1, the inverse of 1 plus all connected geometries divided by disconnected geometries. Now, as long as the connected contribution is suppressed, which is actually true in both de Sitter and ADS, as long as we don't scale the boundary conditions J with an exponential of G Newton, this transition probability turns out to be exponentially close to 1. So all states that you're studying here are almost parallel. So this drastically differs from the traditional Hartle-Hawking analysis, and I'll leave a further discussion on why this is the case for the discussion. So to summarize, we discussed two approaches to computing inner products using the gravitational path integral, the statistical approach, and the Marolf-Maxfield approach. Both approaches require the same non-trivial positivity constraints for Z. We've shown that for closed universes, these are satisfied, and we don't currently have any counterexamples. This is not guaranteed by our current understanding of ADS-CFT. So this is somewhat of a miracle, in my opinion. Using the constructed Hilbert space, you use Bohr's rule to revisit the computation of transition probabilities in the no-boundary proposals. And regardless of the approach that we took, we got answers that completely differ from all past analyses of the Hartle-Hawking wave function. So I just want to leave these as a few discussion points that I have some partial answer to. For positivity constraints, we can ask whether closed universe what is the closed universe positivity with other boundary conditions? whether independent of gravity, these new constraints that we found can serve as useful numerical bootstrap constraints. And this is an example of an inequality that I think is useful. Whether there is some relation between closed universe positivity and S-matrix positivity, and I have some comments about that. Can we constrain from this from the positive semi-definiteness of the inner products and closed universes? Can we constrain the low energy effective field theory and gravity? And related to the closed universe Hilbert space, what are the operators in the Hilbert space of closed universes, and which ones can we actually observe, assuming that we live in a closed universe? And in my opinion, this is where this was what served. This was the inspiration that we had for our proposal for observers. And finally, what is the wave function of closed universes in other natural states, such as maximally mixed states or in alpha states? And one interesting thing is that it seems that the likeliest size of the universe in this case scales exponentially with 1 over g Newton. Okay, thank you very much.
Thanks, Luca. So you said that you bet that the 3D gravity existing calculations won't satisfy this semi-quenched entropy constraint. I guess 2 questions. 1, why do you bet that? And 2, can't we just check it? Like we have the Maloney-Witten partition function and we have the Cotler-Jensen wormhole. I mean, can't we see if those things
They
don't satisfy it?
No, I was saying even with additional ingredients like light matter fields.
Beta by adding stuff, but you don't do
roughly
something.
speaking, the only way to really satisfy it is to get a discrete spectrum.
That seems like.
And I don't think any proposals are sufficiently powerful to do that. For instance, the most promising proposal, which is to include off-shell geometries. We have a model for that in JT gravity, it's just including defects. But the sum over defects doesn't produce a discrete spectrum. It just slightly shifts the spectral edge, but still leaves the spectrum to be continuous. So I think this is a negativity problem in 3D gravity that we will live with for a long time. I hope it's a short time, but I don't know.
Seems hard.
Yeah. Could you say more words about the likely size of the universe?
Roughly. The easiest to explain would be in a maximally mixed state. So in a maximally mixed state, we're just essentially computing the overlap between 2 states, right? Because we're just inserting the identity in between. And, in principle, if there's no non-perturbative corrections important at any value of j, then the distribution of universe sizes would be homogeneous over all sizes. Now, what happens is that when you scale the size of the universe to be of this order, then there's other contributions that become important in the inner product between 2 closed universes. An example of this was the result that Pratik and Stefano discussed this morning. In JT gravity, when you scale the size of the boundary beta to be of order e to the 2s not over 3, then you're seeing that inner products get modified at this scale. So the only statement is that your probability distribution in a maximally mixed state is roughly flat up to you get to these scales where non-perturbative effects can kick in. And because of that, if you have a homogeneous distribution on small scales, but something non-trivial happens on a larger scale, you would guess that the likeliest size is of that order.
I was asking about our universe.
This was all in toy models. I don't know. The issue is that I think to determine this for our universe, you would have to essentially find the analog of these wormhole corrections that Stefano and Pratik discussed in higher dimensions.
I'll ask you the same question that I asked Stefano this morning. Do you have a hunch as to why these wormholes discretize the spectrum?
Do I have a hunch why these wormholes? Well, when we resum these wormholes, we're looking at more and more detailed statistics, right? And eventually it's feasible that if when we go to an extreme regime, like a regime where this inequality might be violated, that these wormhole corrections that save this inequality would be sufficient to show that the spectrum is discrete. But I don't have an intuition for why the resummation of wormholes makes it such that this inequality is satisfied.
So in JT gravity, there exists this canonical quantized Hilbert space. Yeah. And there's this map by Jeff and Witten Edward from the Marolf-Maxfield Hilbert space to the canonical quantized Hilbert space. And I think the projection operators in those Hilbert space still obey the old, what you call the old rules, with additional some global constraint, but you don't see it in simple topologies.
Okay.
And those are the operators that do not compute this alpha. Not diagonal in alpha basis.
Yes.
So I wonder, like in the last part of your question, whether we should modify the probability of seeing our universes. We should actually think about how to understand those canonical quantized Hilbert space, the relation of that to the Marolf-Maxfield Hilbert space.
You mean whether there's a isometric or non-isometric map between them and to define states? Yeah. I agree that's an important question. But I'm not sure that that would answer the probability for what we see. I think for that, we really have to understand what the operators that are relevant for describing our observations are within this Hilbert space. And it's not clear to me that there are operators that you can write down, like the min-cut operator that I think you alluded to, that measure properties of multiple disconnected baby universes, right? And I'm not sure that there exists an observer that can measure the properties of multiple disconnected baby universes. So my only comment here is that I think we should come up with a framework to understand which operators in the Hilbert space we can measure, and then find the eigenfunctions of those, and then figure out whether we should apply the Bohr rule or not.
Do you have an idea why the gravitational path integral seems to automatically give you the closed universe positivity? You said it wasn't obvious, like it would be in quantum field.
Yeah, maybe one intuition that I have, but I'm not sure it's correct, is that maybe this positivity is linked to whether or not the two slices are homotopic to each other. This fails in the open universe in the sum over SL2Z images. But I think it's still true in the closed universe when you sum over the mapping class group. There's like some smooth transition from one closed universe boundary to the other closed universe boundary. But for the open universe, when you sum over SL2Z, there's no smooth way of taking the bottom open universe state to the top open universe state. So I kind of think it's related to that, but I wasn't able to prove it.
Last question.
Yeah, well, I asked you Monday, but I didn't have time to think about it. For instance, people have these matrix models for the sitter JT. Are those positive? Do you know this or not?
Sorry, which wormholes? The proposals. We don't know. Yeah, there are some points of confusion that I have there. For instance, I think they take the matrix integral to not compute norms, but rather transition amplitudes. They somehow make this distinction and keep all their states to be delta function normalizable. Perhaps I'm misunderstanding, since Jordan is here, he can correct me. But I'm not exactly sure what the rule is for computing inner products in those proposals.
Okay, with that, let's thank Luca.